Over the last several days of class, we've talked about a couple of different models of the atom that we've seen through history. The first model was the Dalton solid sphere model of the atom. That was a pretty easy one. The atom is indivisible. The atom is a solid sphere, like a billiard ball, a pool ball. Now, each pool ball is a little bit different. There's an 8 ball, and there's a 2 ball, and there's a 9 ball. They're all a little bit different. Carbon is different from nitrogen, which is different from lithium or sodium. But you can't break it down any further. It's as small as it gets. Then, in 1897, J.J. Thompson discovered the electron using the cathode ray tube. And when he discovered the electron, he had to come up with a model of the atom that put that electron inside the atom. His model of the atom said basically that the atom consists of a sea of positive charge. It's a swimming pool. It's the water in a swimming pool. And the little toys that are floating around inside the water are the electrons, the negative charges that are floating around in a sea of positive charge. That's a big deal. Okay, it doesn't look at all like the model of the atom that we currently accept, but it's a big deal because it's an acknowledgement that there's something inside the atom. There's something smaller than the atom. Well, yesterday we took a look at Rutherford's model of the atom, the planetary model of the atom. It said that the atom consists of a small, dense, positively charged nucleus with these negative electrons. They're still there, but they're orbiting around it in circles instead of just floating around wherever they want. How did Rutherford come up with his model of the atom? Well, we had this box. Inside this box was what we call a scintillation screen. Okay, the inside of the box was basically this scintillation screen that would glow when alpha particles struck it. Inside this box that glowed when alpha particles struck it was another box. And inside this box was a source of alpha particles. It's not a box of alpha particles. It's a box of radioactive material that decays into alpha particles. When it decays, the alpha particles go out the little hole in the box, like this, towards a really, really thin layer of gold foil, right here. Now, Rutherford and his assistants made 3 observations here. The first observation was what? Most of these alpha particles did what? Went straight through. Most of the alpha particles did this. They mostly went straight through. What does that tell Rutherford and his assistants about the structure of the atom if most of the alpha particles that were fired at these atoms of gold foil went straight through? Most of it's empty space, just like the football field analogy we used, right? Okay, that told us that most of the atom is empty space. Now, that's not all of the alpha particles. Some of the alpha particles, when they struck this gold foil, did what? They deflected. They changed direction. Some of them deflected more than others. Some of them deflected a lot. Some of them deflected a little bit. But there was still quite a few. Not most. Okay, most of them went straight through. But there was still a significant number that were deflected. What did that tell Rutherford and his assistants about the nature of the atom? That there's got to be something positive in there that repels them. Okay, something has to repel these positive alpha particles. That must be small. It's got to be small and positive. Small because most of the atom is empty space. Positive because it's got to repel a positive alpha particle. We're going to call it a small, positive nucleus that's in the middle of this atom. Finally, there were a few alpha particles, not very many, but a few alpha particles that did what? Yeah, good. A few alpha particles bounced back like this. What does that tell him and his assistants about the structure of the atom? Yeah, the nucleus is dense, or the nucleus is heavy. So now not only do we have a small positive nucleus, we have a heavy, or we have a dense nucleus. The analogy we used yesterday about the people running across the football field worked pretty well for us, I think, right? You run across the football field, you bounce back, you must have hit something heavy. Maybe it was an offensive lineman. Maybe it was a little 2-year-old kid. Well, if it was the offensive lineman, you bounce back. If it's a 2-year-old kid, What happens? You keep going. If it bounces back, it's got to be heavy, not something light. Adult question? Yeah. It could actually bounce straight back. It just depends upon exactly where it hits it. The nucleus is small, but it still takes up space. It's still got a volume, right? So if it hits it straight there, right there, then it should bounce straight back. But if it hits it kind of off to the side like this, it could bounce back like this, right? It's like playing hockey, okay? We all love hockey in this country, or at least we all should. Otherwise, we should move to another country if we don't all love hockey. Okay, you take a slap shot at a net, hit the post. Okay, sometimes that's going to bounce straight back out towards the blue line. But most times, you're not going to hit that post perfectly straight on, right? Most times you're going to hit it slightly off to the side. And what happens when you hit it slightly off to the side? It bounces back, but it bounces back at an angle, right? Does that make sense? It could. Yeah, it could. But remember, the nucleus is heavy. So just like the hockey puck could jar the net, conceivably, it's not going to move it very much because it's so heavy, right? You're talking about an alpha particle with 2 protons and 2 neutrons hitting a gold nucleus. I'm not even sure what the mass number of gold is, but it's much bigger than 4, much bigger than the alpha particle. Okay? Well, next we went to the Bohr model of the atom. That's the last model of the atom that we've looked at, the second to last model of the atom that we will look at. The Bohr model of the atom had 3 things that differentiated it from the Rutherford planetary model of the atom. The main thing was what? 2 words. Electron levels. Okay, that's the main thing that set it apart. Electron levels. Each of those electrons that orbit around the nucleus orbit around on very specific levels. And each of those levels is characterized by a very specific amount of energy. Okay, the energy of the first level, electrons orbiting around here. Then you got another level out here with a different amount of energy as the electrons orbit around. Okay, now each of these levels also has a limited number of electrons that can exist on it. Okay, it's like the sections of a hockey arena. Right? We have, say, 12,000 people that can sit in the first deck of a hockey arena, let's say. You can't have any more than that because you're limited by the number of seats you can have. Maybe you've got 7,000 in the second deck of a hockey arena. Okay, you can't have any more than that because you're limited by the number of seats you have. Okay, electrons orbiting around the nucleus exist in levels, but each level has only a certain number of electrons that are allowed on that level. And just like a hockey arena, we always want to fill those inner levels first, those bottom levels first, the ones that are closest to the ice first. The second aspect of the Bohr model of the atom was this idea of stationary states. Each electron, as it orbits around the nucleus, is in a stationary state. What does that mean? What's the idea of the stationary state mean? The word stationary, that's what kind of leads you to this, right? As the electrons orbit around the nucleus in a circle, they accelerate. What kind of acceleration do they experience? Centripetal, toward the center. They're not speeding up, they're not slowing down, they're changing direction. But as they accelerate, according to Maxwell, they should emit EMR. If they do, then they're going to lose energy. And if they lose energy, they're going to slow down and spiral into the nucleus like this. Do they do that? No. If they don't do that, then they can't emit EMR. If they don't emit EMR, then something's up. It's like they're not moving. Because if they're moving in that circle, they should emit EMR, but they don't. It's as if they're stationary. They're in a stationary state. Finally, the third aspect of the Bohr model of the atom just talked about electron transitions. Electrons can jump to a higher level, and electrons can fall to a lower level. When they jump to a higher level, what has to happen? They have to what? They have to absorb energy. Okay, they don't just go to a higher level without absorbing energy. Okay, if you didn't absorb energy, you wouldn't be able to climb those stairs if you never ate breakfast in the morning. Okay, electrons need to absorb energy to jump to a higher level. Normally, what form of energy is that in? It's usually in the form of photons, EMR. Okay, EMR of a particular frequency and energy gets absorbed, electrons make a transition corresponding to that amount of energy to a higher level. What about falling? When electrons fall from a high level to a low level, what happens? They give off energy. What form of energy do they give off? EMR. They give off a photon of infrared, visible light, or ultraviolet light. Okay? That's where we finished off yesterday. Today we're going to go a little bit further with that. You see a diagram in your notes and up on the board right now. On the board, fortunately, it's in color. In your notes, unfortunately, it's in black and white. But I think you get the idea there. There's three pictures here. I want to separate the first one from the last two. The first one doesn't really have anything to do with atomic transitions per se. The first one is simply a reference diagram. In the first diagram, we have a solid, a hot solid, or it could be a hot liquid, although in this case it's clearly drawn as solid. Okay, it could be a hot solid, it could be a hot liquid, it could even be a hot gas under high pressure. In all three of those cases, you will get all types of EMR produced. You're going to get every conceivable frequency of EMR produced. In other words, you're going to get true white light. It may appear kind of slightly yellowish. Right? We look at, light that comes from a light bulb. It looks kind of yellowish, right? But we call it white light. It's all the colors of the spectrum. Now, we don't observe it as a rainbow. We observe it as whitish or yellowish light. But if we put a prism or we put a diffraction grating in between a screen and the source, either a prism or a diffraction grating, then what happens? It splits it up. It splits it up into a continuous spectrum, a rainbow, because we had all the colors of the rainbow. Okay, if all the colors of the rainbow were incident upon this, then you're going to get this continuous spectrum produced when we shine it through this prism or diffraction grating. Now again, that doesn't really have anything to do with atomic transitions. The last two diagrams do. We're going to compare these diagrams down here, though, to the first diagram that we just drew. Now in the second diagram, we have a hot gas. This gas is at a low pressure, a hot gas under low pressure. When that exists, electrons will make transitions from high levels to low levels. Hot gas at low pressure has electrons in elevated levels. Okay, those electrons will fall to lower levels. And when they fall to lower levels, they will give off photons of EMR, but not every frequency of the EMR. If there's 7 transitions taking place, there will only be 7 photons produced. If there's three transitions that take place, there's only going to be 3 photons that are produced. Now, when we look at this light, if we look at a light that is produced by atomic transitions, for instance, take a look at the lights above you right now. That's the way they're produced, by atomic transitions taking place inside those bulbs. If we look at that, we don't see specific photons. We still see what looks to be white light, what looks to be all the colors, but it's not all of them. It's just a number of colors that are kind of combined that make it look like white light. But when we stick a prism or a diffraction grating in between a screen and that hot gas that produces those photons according to those transitions, we're no longer going to get a continuous spectrum out the other side. We can't. If we only have certain photons that are produced by this hot gas, then when we go to split up those certain photons, we're only going to get certain photons produced on that screen. We get a red one here and a yellow one and a couple green ones of slightly different frequency, blue and indigo and a violet. Each of those photons that you see there correspond to a different transition that took place right here. If we stand right here and observe it, what do we see? White light. If we stand right here and observe it, what do we see? The different colors, because it's split apart by the prism or diffraction grating. Make sense? Okay, again, in that first diagram, okay, that was a continuous spectrum because this made all colors of the rainbow. This doesn't. This makes just a few corresponding to different transitions. Now, we've simplified this diagram just a little bit here. I said you put a prism or you put a diffraction grating in there, this is what you're going to get. There would be a bit of a difference. Okay, there would be a bit of a difference. One of the differences between the prism and the diffraction grating is that the prism would produce one spectrum. The diffraction grating would produce multiple spectra. This would be, if it was a prism, this would be what you'd see. If it was a diffraction grating, this would be the first order maximum, and then a second order maximum would be over here somewhere, and then a third order maximum, and so on and so on. Make sense? The second difference is that red light is refracted the least in a prism. Blue light or violet light is diffracted the least in a diffraction grating. So the patterns are backwards. Prism, diffraction grating, the patterns are backwards. You guys learned about that in the last unit, right? What about this third diagram here? This is our emission spectrum. Sometimes we call it our line emission spectrum. The third diagram, you can see it's called an absorption spectrum. If we take away this cold gas, what do you got? You've got the first diagram. You've got a continuous spectrum, right? It has nothing to do with atomic transitions. Right here, we've got a hot solid, a hot liquid, or a hot gas under high pressure. It produces all the colors of the rainbow. And if we put that through a prism or diffraction grating, we're going to see a continuous spectrum. We're going to see a rainbow. But if we stick a cold gas in here, then no longer do we see a continuous spectrum over here. What happens? What's this cold gas doing? It's taken away certain kinds of light. It's taken away certain photons because it's causing the light is being absorbed by the cold gas, causing the electrons in lower levels of the cold gas to jump to higher levels. So you don't have a continuous spectrum on the right-hand side anymore. You have a continuous spectrum minus a red photon that was absorbed by the cold gas, causing an electron to go to a higher level. You don't have a yellow photon because it was absorbed by the cold gas. Or these two green ones were absorbed by the cold gas. The blue, the indigo, the violet, all absorbed by the cold gas, causing electrons in the cold gas to jump to higher levels. What do you notice about these two diagrams? The line emission spectrum is produced by hot gas under low pressure, electrons falling, and the absorption spectrum that's produced by the cold gas absorbing photons, causing electrons to jump. What do you notice about those two spectra? They're exactly the opposite of one another. What does it tell you about those two gases, the hot gas and the cold gas? Well, one's hot, one's cold. In that sense, they're opposite. If this hot gas is helium, then this cold gas must be helium, just cold helium, because hydrogen would produce a different spectrum. Hydrogen has different transitions that take place. Lithium, sodium, all the other different elements would produce different spectra because they all allow different atomic transitions. We can identify unknown gases based on their spectra. When I went to university, my first year, I remember having not done any of this stuff in high school. You guys are ahead of where I was at this point. I had never seen this stuff in high school. When I went to university, one of my professors spent his entire academic career studying, observing, and photographing atomic spectra. That's it. That's all he did. He taught a couple classes, and he photographed atomic spectra. And I remember when I first found that out, when I first saw his lab, I remember thinking, for what? Like, why would you ever, like, what benefit could that possibly be to take pictures of this atomic spectra? Okay, somebody explained to me that my professor was his passion in life was physics, but he was kind of an amateur astronomer as well. At home, he loved astronomy, and he looked at stars and did whatever. And one of the reasons that he chose this avenue of physics to look at is because it's so relevant to astronomy. Let's say you're looking up at the stars. This is what you do for a living. You're an astronomer. You look up at the stars and you find a new star that nobody else has ever found before. Okay, nobody else has ever seen this before. And you say, wow, like this is huge. I'm the first person in history to see this star. I wonder what this star's made out of. We can't just get on a ship and go to the star, collect a little sample in a bottle, and then come back and analyze it. So how do you find out what it's made out of? You look at it. You look at it through a prism or a diffraction grating. In other words, you look at it through a spectrometer. You observe the spectrum that's produced through that prism or diffraction grating. If it looks like this, what does that tell you is present in that star? It would be that hot gas. In this case, it would be helium, right? If you see something different, it tells you that something else is present in that star. But unless you have something to compare it to, that doesn't help you. If I can see this spectrum, and I don't know that this spectrum is produced by helium, then it doesn't really tell me anything. So you've got to have guys around the world that are taking pictures of these so that you have something to compare it to. There's lots of other applications. Any time, basically, that you want to know the composition of an unknown gas, you can do spectroscopy on it. You can look at the spectrum that's produced by that unknown gas and compare it with known spectra. And you can determine what's in it. For instance, we get three spectra here. There's hydrogen, a hydrogen known spectra, a known helium spectrum, and a known sodium spectrum. You can see that they're all different. It'd be nice if these were in color, actually, but they're not. Three different spectra. You can see that they're clearly different, right? Lines in different places. We also have an unknown gas mixture here. We want to determine what this unknown gas mixture is. We look through our spectrometer at a star that was recently discovered. It's our job to try to figure out what's in this star. We see this spectrum that's at the bottom. We compare it with known spectra of hydrogen, helium, and sodium, and we try to determine what's in it. Can you tell me what's in it? What's one thing that's in it? There may be one thing, there may be two things, there may be three things. What's one of the things that's in it? Emil? How do you know that hydrogen's in it? Yes, not just similar, has to be exact. All of the lines from hydrogen have to be in there. Are they? Yes, they are. And there's some extra ones as well, right? We have a couple extra ones here that aren't in hydrogen. That's okay. If all of the lines of hydrogen are in there, then hydrogen must be present there. So one of the things that's present in this star that we just discovered is hydrogen. What else? Let's take a look at helium. Are all the lines for helium in that unknown gas? No. Looks like one of them is. Is that enough? No, we need them all. So that doesn't work. No helium in there. Okay, good. We know this star contains hydrogen, which makes sense for a star, right? We know that it does not contain helium. What about sodium? Well, those two lines of sodium are there, so sodium must be present as well. Is that a hard question? Somebody this morning in period 1 said, boy, I hope we get something that easy in our diploma exam. This was a diploma exam question. I literally copied this from a diploma exam. It was about 12 years ago. But it was still a diploma exam. It was question number 50, the last question on a diploma exam. Good way to end the exam, eh? Now, if this ever appeared on an exam, it would be in color, which would make it even easier than it was back then, because everything was all black and white then. Of course, you'd wait to page 50 to see the color. It is exciting, though, when you see that color. You know, there's usually 1 or 2 questions in the exam that have color on them. That's it. And when you flip the page and you see that color on page 27, it's like, I don't know, it brightens your day. You have 3 minutes left to write it's 11:27 in the morning, you have 3 minutes left to write the exam. You have 16 questions left, and at least you just saw some color. At least you're happy for that reason. No, it won't be that bad. The picture you see up on the board now is a little bit more abstract. Okay, the pictures that we saw up on the board just a minute ago, these are what you actually would see, like physically with your eyes would see as a result of different atomic transitions. What you see up on the board now is a representation of atomic transitions. It's a good representation, though. We call it an electron level diagram. And then you can see that it shows a number of things. First of all, it shows all these different levels at which electrons can be. This would be the nucleus. Okay, this would be the first level above the nucleus, second level, third level, fourth level, fifth, sixth. You can see as we get higher levels, they get closer and closer together. Okay, that's supposed to be. This is drawn to scale, roughly. Okay, the electron levels get closer and closer together as they get further and further away from the nucleus. You can see that I've stopped drawing them at the 6th level. That's not because there isn't more than 6 levels, but simply because they get closer and closer together and it becomes really difficult to draw them. The dotted line up here is what we call the infinite level. That's when the electron has essentially left the atom. It's become ionized. It's gone. It's not really part of the atom anymore. You can see on the bottom here, we've named the different series. When an electron makes a transition to or from level 1, we call it Lyman. To level 2, Balmer, Paschen, Brackett. You don't need to know those names. These numbers that appear on the left-hand side are the energies of the different levels, specifically for hydrogen. You could see a diagram like this for any element. The only difference would be the names on the bottom wouldn't be Lyman, Balmer, Paschen, Brackett, and the numbers on the side wouldn't be the same numbers. The same structure of the diagram would exist, though. It would look the same other than the numbers and the names on the bottom. I want to take a closer look at the numbers for hydrogen here. What do you notice that seems a little bit odd about those numbers? Or do you notice anything that's odd about those numbers? Emil? They're negative. Why are they negative? And why do they get bigger as they get closer to the nucleus? You would think that they would get smaller as they get closer to the nucleus. Let me give you a little analogy here. Let's say that the Earth is the atom. Okay, the core of the Earth is the nucleus. So here's our Earth. Here's the core of the Earth, which is our nucleus. You're standing outside of the Earth. In other words, you're outside of this atom. You're an electron that's become ionized. You're gone from the atom now. Okay, you're gone from the Earth. If you happen to climb a ladder up, you would gain a certain amount of potential energy that would be equal to mgh. It would be positive, right? But if you drilled a hole down to the core of the Earth, like this, and you started climbing a ladder down towards the core of the Earth, your potential energy wouldn't be positive something. It would be, relative to the surface of the Earth, would be negative something. And the further down you went towards the core, the bigger that number would become, right? When the electron has become ionized, we consider that to be energy is equal to 0. As we go down towards the nucleus, it's like we're going down that tube down towards the center of the Earth. The potential energy of the electron becomes negative, and it becomes bigger as we get closer and closer to the center. Does that make sense? Okay, so what are we going to do with this picture, this diagram? Well, there's a number of things that we can do with it. One of the things, they all tend to be fairly easy, by the way, as well. One of the things that we can do with it is determine how much energy is emitted, how much energy is produced or fired off in the second line of the Balmer series. The second line of the Balmer series, if we go back to this picture, would be right here. Okay, first line, second line of the Balmer series. If you want to find the energy that's released or emitted in the second line of the Balmer series, don't make it harder than it has to be. The final energy here is neg 3.4 electron volts. The initial energy is neg 0.85 electron volts. Negative 3.4 minus negative 0.85 gives me negative 2.55 electron volts. How much energy was released in that transition? Because it's negative, it tells us that it's released. It's 2.55. What if I had have asked you how much energy is absorbed when we go from 2 to 4? What would the answer have been? Positive 2.55. If it's negative, it's released. If it's positive, it's absorbed. Although, to be honest, if you got a question like that asked on an exam, they would probably ask you for the magnitude of the energy as opposed to positive or negative. You weren't asked this in this question, but let's pretend you were for a second. What if it said, what was the frequency of EMR released? What was the frequency of EMR produced here? Anyone want to take a stab at that? It's not a hard question. When an electron makes a transition from 4 to 2 or any other higher level to lower level, a photon will be given off. The energy of that photon is the difference in energy between the levels. The frequency is simply going to be found by taking the energy of the transition, 2.5 electron volts, and solving for the frequency. If you wanted to find the wavelength, you do almost the same thing. You got the energy of the transition, let's solve for the wavelength. So what do we use these numbers for? The only thing we ever do with these numbers is subtract them. Don't ever plug in 3.4 or 0.85 in for this energy. Don't ever do that. You can subtract those numbers and then make the difference equal to E over here. But these numbers are only good for subtracting. It's the difference in energy we want for these energies over here. Okay? Is that okay? What about this one? 2 more examples, then that's it. Determine the ionization energy for an electron on the first level of hydrogen. Let's go back to our diagram. The ionization energy. What's that mean? The energy required for the electron to leave. You're deep within the Earth. What's your ionization energy? The energy that's required to get you to the surface. Okay, the energy that's required for the electron to go up here to the infinite level. Tell me what it is right away without even doing a calculation. You're at neg 13.6. What do you got to absorb to get yourself to 0? 13.6. Okay, 13.6, done. 0 minus negative 13.6 equals 13.6. And finally, one more question that appears in your textbook on 775. How much energy must a hydrogen atom absorb in order for its electron to move from the ground state to the third level? From the ground state to the third level. From the ground state to the third level. Okay, that would be the second line of the Lyman series, except it's absorption instead of emission. Well, EF minus EI, again, we're going to say neg 1.51 electron volts, subtract neg 13.6 electron volts. That gives us positive 12.09 electron volts. Notice it's a positive value. So it's negative if it's given off, emitted, positive if it's absorbed. Let's see what we can do with these two. A couple little things. First of all, the diagram that we have is in electron volts. So be careful here. They're asking for the answer in joules. So you know what you're going to have to do there, convert after the fact, right? The other thing is that this answer has a typo in it. It should be 4.56, not 4.58. So let's see if you can get 4.56 for the second one. Okay. Well, those ones seem okay to you. Let's try this one, okay? This isn't quite a formal electron level diagram, but it's pretty much. It shows you the electron energy levels. So let's see what you can do with this. Use the same process that we went through, even though it's not quite as detailed as a diagram. How many people get A for this? B? C? D? Okay, the answer is A, yeah. All we're doing is subtracting the two energies here, and then setting E equal to H times F. Make sure when you set E equals H times F, you make H 4.14, because we're dealing with the electron volts, right? If it was joules, you'd use the 6.63 value. Good?